So you're all set? Okay, then it's my pleasure to announce the next talk in this event, and it's by Ashvni Narayanan, who is now at the University of Sydney and will tell us about the formalization of p-adic functions in Lean. So go ahead.
Thank you. Sorry, that is a typo in the title. It should have been p-adic functions.
Yeah, I wanted to say that because it just that's how it rolls. Okay, anyway, go ahead.
Thank you. Thank you for inviting me for this talk. And I will be talking about this paper, Formalization of p-adic functions in Lean 3, which I have now been trying to also port to Lean 4. So I'll tell you a bit about that. And it's pretty simple. I'll tell you what p-adic functions are and their implementation in Lean 3 and Lean 4. Okay, so to give you a bit of background, we begin with the Bernoulli numbers. A lot of you might know about the Riemann zeta function. It's a little famous. And the special thing about, one of the special things is that the Riemann zeta function takes some special values in terms of Bernoulli numbers at negative integers. This is the Bernoulli number Bn. And they are generally generated using these generating functions. But the interesting thing about them is that they appear in various, you'll see them everywhere in number theory and also in other spheres of mathematics. So for example, one interesting formula is Fowler-Haber's formula, which tells you the sum of consecutive powers of consecutive numbers in terms of these Bernoulli numbers. Okay, and then we have the Bernoulli polynomials, which are generalizations of these Bernoulli numbers, and they are defined in Lean as this. So I forgot to mention, but Bernoulli numbers were defined in Lean by Johan, and I added a few properties regarding them. So these are rational polynomials in terms of Bernoulli numbers. And the point of interest for me is this generalized Bernoulli number, which corresponds to a Bernoulli number twisted by a particular Dirichlet character. I will get to the definition of a Dirichlet character in a second. But again, these are they come from generating functions of this form. And when chi is trivial, you can see that you regain something in terms of the nth Bernoulli number. And here, if you know something about Dirichlet characters, then you know that every Dirichlet character has a conductor. And there is a particular property that for any multiple of the conductor, you have this particular formula of the generalized Bernoulli number in terms of the nth Bernoulli number. So this, I think, was the easiest way to define the generalized Bernoulli numbers, because this is not a very workable definition. And so the the capital F that I choose is simply the conductor. Also note that the general definition is for primitive Dirichlet characters, but our definition here works for any Dirichlet character, because we simply look at the primitive character associated to any Dirichlet character. Okay, so that's about Bernoulli numbers. Let's now understand a bit about p-adic functions. So there is this congruence called Kummer's congruence, which says that given any two positive even integers, which are not divisible by p minus 1, where p is a prime, you have this congruence to be true mod p. And so Kubota and Leopold were trying to study this congruence, and they were looking for a meromorphic function which would help understand this. And this is where they landed upon the p-adic function, which is basically a meromorphic continuation of these numbers at the negative integers. Sorry, what I mean is that the p-adic function takes this particular value at the negative integers, and if you remove this p term over here, then you will end up with the Dirichlet L function. Okay. So how do we go about defining this in Lean? One problem is that when we speak about meromorphic continuation or extension, we mean extension into CP, which is the p-adic closure of the algebraic closure of ZP. And so, oh no, sorry. The p-adic closure of QP and the algebraic closure of that. That is what CP is. So anyway, the point is CP did not exist in Lean at that point of time, and it is not trivial to define CP. So I had to find another way to go about this, and the answer came from a theorem in Washington's book, Introduction to Cyclotomic Fields, in which he said that the p-adic function is equal to some value in terms of a p-adic integral. And that is how we ended up defining it. Okay, so this is the definition. We have the Dirichlet character, the Teichmuller character, the weight space, which is nothing but continuous monoid homomorphisms, the p-adic integral, and the Bernoulli measure. And I'll say a little bit about all of these. Okay, so what is a Dirichlet character? A Dirichlet character is generally a group homomorphism into C. And in Lean 3, I defined it as a monoid homomorphism from Z mod NZ star to R star for some particular level N associated to the Dirichlet character. Okay, so this was the definition in Lean 3. And in Lean 4, this is what the current definition is. So the change over here is that instead of looking at it as a monoid homomorphism from Z mod NZ, from the units of Z mod NZ to the units of R, we look at it as a monoid homomorphism from Z mod NZ to R, which is 0 on the non-units. It's they are both equivalent, and yes, so the thing then is to translate all of the code from the units to Z mod NZ, which is in fact better because it requires less work in a sense. Okay, and then we have the Teichmuller character. Oh, sorry. Yes, this is the Teichmuller character, omega. And a fun fact is that it's a very easy thing to define in terms of Dirichlet characters. But because the width vectors already existed in MATLAB, I simply used width vectors to define it, which is a lot of heavy machinery and probably unnecessary, but it's fun and it made life easy. Okay, so then I'll tell you a bit about p-adic measures. So a p-adic distribution is simply a linear map from the space of locally constant functions of a profinite space to the image, which is in a normed commutative ring. And a p-adic measure is basically a bounded distribution. So if you're given a locally constant function, then the norm of phi of f must have a bound in terms of norm of f, where here the norm is the supremum norm. Okay, so this is a relatively straightforward definition. And the inclusion here is the function from the inclusion of the locally constant functions into the space of continuous functions. Okay, so this leads us to the p-adic integral, where if you take any locally constant function and a p-adic measure phi, then you can just define the integral to be the evaluation of f at phi. And I proved that for when x is profinite, then the space of locally constant functions is actually dense in the space of continuous functions. And so the integral can be extended linearly onto the space of continuous functions. Okay, so that gives us the p-adic integral, and then we need to make a choice of a p-adic measure, and that measure is chosen to be the Bernoulli measure. And because we are working on this set, special set Z mod dz cross zp, where d is co-prime to p, we have this Bernoulli measure here. It can be defined on these Clopin sets, and that is sufficient because our space of p-adic integers actually has a Clopin basis. Okay, so we define it in this way. And the definition is a bit complicated in terms of eventually constant sequences, blah, blah, blah. Yeah, but what I want to show you is that from this definition in Lean 3, a lot of things go out in Lean 4. For example, this mul prime power pause goes away, and it can actually be inferred by the system, which is great. Okay. So now that we have this p-adic L function, we actually want to see that it satisfies this property that we started out with, that is its evaluation at negative integers. And this is very computational in nature. It does depend a lot on the following special property of generalized Bernoulli numbers. And this is very interesting in the sense that actually, maybe I can show you. I don't know if, let me know if you can see the screen change. So this is the book Introduction to Cyclotomic Fields, which I was following. And this is the formula that I just told you was the definition. And what I'm using is this lemma over here, which you can see looks a bit like the formula I just showed you, but it's not the same. And this is because our original theorem here has no, it does not say anything about what chi should be. So any Dirichlet character can be either odd or even. That is, chi of -1 can be either 1 or -1. But if you look at this lemma here, the hypothesis is actually that chi is an even Dirichlet character. And so the odd case was not considered. Thankfully, it is easy enough to make it work. You only get this extra term here, which turns out to be 0 when chi is even. So that worked out well. And yes, so now let me show you a bit of Lean code. I'm sorry, I'm going to show you Lean 3 code because the files are all there. Okay, so first, this is the definition of the p-adic L function. And you can see that we have, to begin with, a prime P, natural number D, a normed commutative ring R, D is co-prime to P, chi is a Dirichlet character of level D times P bar M, and C is a number co-prime to D and P. This condition here is the non-Archimedean, is that R's norm is non-Archimedean.
Ashvni,
yeah.
We still see your slides.
Oh,
was it your
I'm so
intention
sorry.
that we?
One moment. I'm sorry.
Okay.
Thank you so much. Is my screen visible now?
No. Yes. Yes. Now we see VS Code. Okay.
Okay. Lovely. So this is the definition of the p-adic L function. where we have all these properties of the normed commutative ring R and the Dirichlet character and the norm being non-Archimedean. And R is a complete normed QP algebra. And the LP is the integral with respect to the Bernoulli measure of chi multiplied with omega power minus n. And this thing here tells you that it is, in fact, a continuous function. Okay, so that is the p-adic L function definition. And this here is the fact that its evaluation at negative integers is exactly what we want it to be, which is 1 over n times 1 minus chi omega power minus n of c power n times 1 minus chi omega power minus n of p power n minus 1 times b n chi omega power minus n. Okay, so I can't delve into too many details because it's a very long proof. And I wanted to show you that actually there are, sorry, one moment. Where is, right. So I wanted to show you the length of some proofs here, which I know is unhealthy and not in line with what MATLAB suggests, but these are genuinely hard things. This was genuinely very hard for me to work with. Oops, sorry. So let me just, sorry, I have it open here, but I can't access it. Right. Okay. So this is the lemma, simply the statement of the lemma, which is about 20, more than 20 lines long. And proving this is not fun. So I don't know exactly how to reduce the size of these proofs. To an extent, they can be compartmentalized, but otherwise I'm not so sure as to how to make this work. All right. Okay. So a few more things that I would like to say. So this took me 2.5 years to formalize. This was actually my PhD thesis. And the code I just showed you has 28 files and about 9,000 lines of code after 3 refactors. The first time it was around 16,000. But the thing that really made a difference was that at some point I started using filters instead of metric spaces. Sorry, so what I mean is that I had to work a lot with limits, and you probably know that limits in Lean are in terms of filters. The filter dot tends to. So a lot of delta epsilon calculations that I need to do, I realized were basically just arithmetic calculations, which could be done using filters, and that significantly cut down the code. Also, instead of CP, this p-adic L function takes values in a normed complete non-Archimedean QP algebra, which is a generalization. The only thing is there is an extra factor which is dependent on C, and that is because I did not assume that our target ring R has division. If it has division, then you can simply divide by this factor and you will get back the original definition. Okay, and like I showed you, the proofs are very heavy on calculations and actually consist of, I would say, even half of the project. So this is a very crude mind map of what's happening. We have the Dirichlet characters, the Bernoulli numbers, which give us these generalized Bernoulli numbers. And then there's the definition and that special property of the generalized Bernoulli numbers, which eventually gives us what we want. And you can see that this side over here has a lot of technical stuff going on, but this side over here really just is calculation, root calculation. Okay, and so to summarize what we have in Lean 3, p-adic L functions, and the following has been ported to MATLAB 4, Bernoulli numbers and polynomials, Dirichlet characters and their properties, which are a very recent addition. And I have some ongoing PRs about the properties of Z mod, which will later be used to prove that the p-adics are profinite. And I'm very bad with PRing. I try my best, but hopefully I should be able to port the rest of the properties of the p-adics and the generalized Bernoulli numbers and everything else, which may actually be very relevant to other projects, other ongoing projects. Yes, so if anyone would like to help me, I would be very grateful for any help I could get. And finally, some small notes about Lean 4, which I noticed. So sums in general were tricky to deal with even in MATLAB 3, but I feel like the simp rewrite has become a little different in the sense that I used it to do multiple calculations at once and to avoid going into conv mod, but that does not work so well anymore. So these are a few things which I did have challenges with. I have managed to port about 20 out of the 28 files, and I expect some roadblocks along the way because the next few files are very sum heavy. And what I did find great was consistent naming and this use of not equal to 0 pretty consistently. Because then you don't need to keep shifting between n positive and n non-zero for any natural number n. And because instance inference was a lot better, I could remove a lot of unnecessary code, which is basically apply instances all over, repeatedly, which was great. In general, I did find my code to be working quicker and there were less deterministic timeouts as of now. And that's it. Thank you, especially to Kevin, who is my supervisor, Filippo, Maria, Anne, Joanne, and Oliver for all their help along the way. And Moritz, who has been helping me PR things into MATLAB 4, and the Lean community, without who I would not have been able to do this. Thank you.
Yeah, thanks a lot for that talk. So I see a first question by Adam. Go ahead.
Hi. Yeah, I'm curious about that lemma statement that was like 45 lines long. Did you write that by hand or did you use like extract goal to get that statement?
No, I think I wrote it by hand.
Oh, wow. Okay. That must have been painful.
Because extract goal, I may be wrong, but if I remember correctly, it gives a lot of coercions, which anyway need to be gotten out and written explicitly. So it would not help either way, not help much in this scenario.
So do you still have that your VS Code window open? Do you mind just showing that statement again?
Sure.
Honestly, it is surprising to have a statement that long.
Yeah, there we go. And this is not, I mean, there are a lot of variables which are missing from the statement.
Right.
Let me.
Well, where's the colon? Well, oh, I see it. Okay. Oh, no, I don't see it.
This is the colon.
Oh, okay. Okay, I see. Uh-huh.
So my memory was that this was a much longer proof that you broke into smaller pieces by continually using extract goal.
I mean, yeah, maybe I could have maybe just gotten the bare skeleton, but then these coercions need to be added in. So let me see. Yeah, so you can
Right.
see
Sometimes
this.
extract goal wouldn't compile.
Yeah, yeah.
And
And sometimes these were just, the original lemma statements that needed to be proved. And for example, the generalized number special property that I showed you is in itself a pretty big statement. So yeah.
But it seems that there is quite some term duplication going on in this statement. Like you just selected something and it showed up multiple places in the statement. So maybe that suggests one way to compress the statement a bit. Like you just create a new variable that you call, I don't know, some fresh name. And then you say, and you add a hypothesis that it's equal to this sub-expression, but then you can replace this sub-expression in many places.
Yes.
Unless that messes up
also
some motive somewhere. But
link for notations and elaborators would help a lot here.
yeah, I really hope that in Lean 4 we can make this a lot better.
So I did use quite
so let me ask
few
a question about that.
Sorry, go ahead. Yeah.
So in general, while you're porting this to Lean 4, is your impression that so you mentioned that it gets faster, and you mentioned some downsides and some benefits, etc. In general, do you feel like it becomes let's say more readable and say shorter or closer to what it looks like on paper? Or do you feel like it's actually the same or maybe getting worse?
It's hard to say. I guess it's a mixed bag. In some cases, it did get more readable, but I don't actually have much hope for statements like these because this, I guess you can keep repeatedly using abbreviations, but in the end, when you unfold them, you're still going to end up with this big, huge thing, which is going to be tough to deal with.
Well, then maybe don't unfold
them. But I think I do need to unfold at some point because these are all different things that are interacting. It's like long sequence of, minus and pluses that cancel out via commutating at different points.
But
actually,
but maybe the hope would be that like you unfold and then give it to a tactic and the tactic cleans
yes,
everything
I
up.
tried that. Unfortunately, that didn't work very well, at least in Lean 3. And wherever I've used ring, as of now, it has failed in Lean 4. So I don't know, but of course I would try to use as many tactics as possible.
Yeah.
I think once you've got a Lean 4 version, you should post it on Zulip and we'll do something. Collectively, we'll manage something, I'm sure.
Thank you.
Okay. Yeah, thanks so much.